method is applied to answer the following question. Find the minima maxima of a function of f. Well, actually, this is in any dimension, but we'll be dealing this only for 2 or 3 dimensions. So find the minima maxima of a function f. Okay, let me write it in general, fp, where p is restricted to the 0 set of some g of p. Okay? So this holds in any dimension. If you want to be fancy about it, we can apply this even for functions of one variable. I can show you that later. But okay, so for us, since we want to draw pictures in calculus, our setup will be the following. So we have a surface, some nice surface like this. Okay, so this is S, our surface. Later, we can do this in the plane also. Our surface given by g of x, y, z equals 0 in R3. We have a function f from here to R. Okay? So we want to find the minima and maxima of this function. Okay? We want to find min-max of this function. Okay, so our setup will be this. A variation of this will be, we will have a curve. Instead of S in R3, we will have a curve in R2. A function which is normally defined everywhere in R2 will be restricted to that curve. And again, the question is to find the minima and maxima. And as I mentioned here, the technique, the Lagrange multipliers technique will apply to any dimension. If you have the 0 set of not only one function, you can consider the 0 set of several functions in Rn. You have a function defined on that 0 set. Up to those restrictions, what is the minima and maxima of the function? Okay, so that is the general question which Lagrange multipliers method is applied. Okay, so let us start here by drawing the picture. So we have this, our surface. So this is our surface S, given by g of x, y, z equals 0. So we don't want arbitrary surfaces. We want nice surfaces. Nice surfaces for us are those which have, technically describing, are those surfaces which have tangent plane at every point. Okay, so we call them smooth. So whatever image you have when we say smooth, we are trying to describe that technically so that we can recover it from the equations. In order to have a tangent plane at every point, we should have the normal of that plane well defined at every point. We know that the gradient of this function is perpendicular to the surface at every point. If it is different than 0, then it defines a unique tangent plane there. Okay? If you have the gradient like this, then if it is non-zero, it is orthogonal to a unique plane. If it is 0, then it is orthogonal to everything, so there is no unique tangent plane. So first of all, we want that. We want this to be a nice surface in everyday language. In calculus, we want the gradient to be non-vanishing at every point on S. Okay, so we want S to be nice. Okay, so in calculus, this means that is gradient of G is different than 0. Well, actually, this is the 0 vector, okay, for all P in S. Okay, so S is smooth. Okay, we say S is smooth. Okay, so I can not write it. Another thing that guarantees that a minima and maxima exists on on the surface S is that S is closed and bounded. Okay? But even when S is not closed and not bounded, depending on the nature of S and depending on the nature of the function f, there may exist a global mean and max. Okay? But that we will leave as a personal check. Okay? You have to interfere to the method at some point yourself. It won't solve everything. Okay? So, okay, I'll write that later. So we have this function f to r. Okay? Obviously, if f is a function which doesn't have any derivatives, then it's not a subject of calculus. We want f to have at least first order derivatives so that its gradient is defined. We can talk about this. Okay, so f has first derivatives. Okay. Now suppose that there is a point here where f takes a local minimum or local maximum. Okay, so this is a typical approach in science. In general, it is not easy to find sufficient conditions immediately for f to have a minima maxima at a point. So we start backwards. We say, suppose there's a point where this function takes a minimum or maximum, at least local. Then what conditions should f satisfy? Okay, and then we go back again. We check at which points those conditions are satisfied. Of course, it doesn't guarantee that this point came from a minima or maxima, but minima or maxima is among those points. Okay, so that's it's just like what we did with one variable case. If there was a maximum, the derivative was 0. So what did we do? We looked at all points where the derivative was 0. So minima maxima was, in most cases, among them. In extreme cases, it occurred at the end points. And sometimes minima maxima can occur at a point where the derivative does not exist. So here we exclude that by saying that the derivative of g will exist everywhere. Okay? And will be non-zero, so the space will be nice. We are saying that this has first derivatives everywhere. So for an easy application of Lagrange multipliers, we are excluding those extreme cases. Okay, so suppose there's a point f has maybe a local extreme point, mean max, at p sub 0 in S. Okay, so here is our point, p sub 0. We'll try to understand how f and g behave at that point so that we can check those things. So, okay, we'll say, okay, I'll put the coordinates later. Now, this means that in some neighborhood around here, okay, let's say f is maximum, f takes a maximum value at that point. In some neighborhood around here, f of p sub 0 is larger than any value of f around this point. So we restrict f to a curve passing through that point. Then obviously, if we now consider only that restrictions, f will again have a maximum at p sub 0. Okay? So let's do it with red maybe. Okay? So now consider this curve C passing through this point. So consider a curve C lying totally in S, p sub 0 in C. Restrict f to C. Okay. Now f restricted to C has again maybe a local min max at p sub 0 in C. Okay, remember that C was in S. Okay. Okay, now this is a good observation. Now we write what we wrote here in words, in formulas, and check what is the consequence of this expression, restricting f to this curve C and forcing the condition that f will have a local maximum or minimum here. So it will be a function of a single variable because I can parameterize this curve by one parameter, say t. When I put that parameterization into f, I get a function of t. if that function of t has a maximum here, the derivative of that function with respect to t is equal to 0. Okay? So that will be our first condition, and then we'll, again, after we write it, we'll stand back and stare at the formula and see how we can make it into a method, and that will be Lagrange multipliers method. So let me do that now. Okay. Now we want to write that in terms of calculus. Okay, so we say, suppose P sub 0 is x sub 0, y sub 0, z sub 0. Parameterize C as position vector t equals x of t, y of t, z of t. T is in some interval. Okay, it doesn't matter which number I choose here. Okay. We said that this is possible because locally where you stand here, you look around, you think you are in R2, just like the Earth. Earth is round, they tell us. But we look around and we see that it is flat. So this is exactly the same thing here. So locally we can put any curve we like here. So that's why I'm restricting here. Maybe it is possible to put a whole curve parameterized with R, but we are only interested locally what's happening around here. We want this curve to pass through this point. So let's say such that R of 0 is equal to x sub 0, y sub 0, z sub 0. Okay, so this is the x of 0. We say that make it this point. Okay, so it passes through here. Again, we want this to be a nice curve. Okay, we don't want this to be a curve like this with the pinch at that point, because we know that derivative behaves strangely at singular points. So we want this to be a smooth curve again, just like this. So we put a condition on this curve, and the velocity vector of t, which is derivative respect to t of r of t, is different than 0, 0, 0 for all t in the interval. Okay, so this condition, remember from last semester, I think we said this says that the curve is smooth. Okay, so that is C is smooth. Technically, a more correct thing would be to say that the parameterization is smooth, because if you have a smooth curve with respect to one parameterization, then you can find a strange parameterization of the same curve, which may not be smooth, because if you parameterize this like this, go back and forth, then obviously that condition will not hold. But geometrically, the shape is nice. So we want both the shape to be nice and the parameterization to be nice. Okay, so what else? Now we wrote everything up to here in calculus. Now we restrict f to this. Okay, so restricting f to r of t. Okay, so this gives a function of t. So let us make it phi of t. This is f restricted to r of t. Okay. Now we write this in full. F of x of t, y of t, z of t. So this is a function. Again, t is in the interval we chose. Okay, so suddenly everything became clear. We'll take the derivative of this. The derivative of this, we'll use chain rule because we have a composition of two functions. And we'll now impose this thing. Okay, we take the derivative of this. The derivative at a local mean or maximum is 0. So that's what we want to do. Okay. Okay. So phi of t has a local mean max at t equals 0. So phi prime 0 equals 0. Okay. So again, we'll do something very typical in science. We calculated phi prime 0 in one way. Now we'll calculate it in another way. I know that phi prime 0 will be 0 because of this consideration. Then I'll take the derivative of phi here and force that equal to 0. So that's another way of writing phi prime equals 0. Okay, then we'll check what we can get. Okay, but we can write phi prime t using chain rule from above definition, description. Okay, so this is the description. So let us write that now. Phi prime t equals, okay, chain rule, derivative of this with respect to its first variable times the derivative of its first variable with respect to t plus you repeat it with the other variables. Okay, so let me write this in full patiently once. Derivative with respect to x. Now I put, okay, so I'll put t, I'll leave this at t, y of t, z of t, x prime t plus, okay, so now the rest I'll just write this, okay, so evaluate it at this point, multiply it by y prime t plus f z, z prime t, okay. If I put t equals 0, this is going to be 0, okay, so 0 equals phi prime 0. Derivative of x evaluated at t equals 0, at t equals 0, okay, so where is this? Here it is x sub 0 and it is p sub 0, so let me write p sub 0 here, times x prime at, okay, so it will be here, x prime 0 plus fy p sub 0 y prime 0 plus fz p 0 z prime 0. Okay. Again, we recognize this as the dot product of two vectors. The first one we recognize. This is the gradient of f evaluated at p sub 0. The other one, this vector. So, okay, so this vector, this vector, this vector is derivative of this with respect to t. That's the velocity vector. So this is v prime. I'm evaluating at 0. Okay, at 0. I know that this vector is never 0. Okay, so I have this thing. Now, if there is a local minima or maxima, then the gradient of f is perpendicular to every tangent vector. Okay, so this is a tangent vector to the surface provided by this curve. If I change the curve, I'll have other tangent vectors. So, okay, we write this thing now. Okay, so we found if p sub 0 is a local min-max for f on S, then first of all we have gradient of f at p sub 0 dot product, so that v sub 0 is a tangent vector to S at p sub 0 is equal to 0. Okay, so this can happen in two different ways. Gradient of f at that point may be 0. Then it will be, the dot product will be 0. If it is non-zero, then it is orthogonal to the surface. Okay, so either gradient of f at p sub 0 is 0, or gradient of f at p sub 0 is different than 0 and is orthogonal to S at p sub 0. At this point, we suddenly remember that there is another natural vector which is always orthogonal to the surface at every point, the gradient of g. Okay? S is given as the zero set of g. By using similar arguments, remember that we showed that the gradient of g also ends up with an equation like this. Okay? So gradient of g is perpendicular to the surface at every point. Okay? You see the difference here. The gradient of G is perpendicular to the surface at every point. Gradient of F will be perpendicular to the surface only at the points where it has a global, it has a local minima or maxima. Okay? Or maybe it is also perpendicular to F at some other point, but no, there I can again pass a curve and I can show that it's a local minima and maxima. Okay? So we have two vectors like this. This is always orthogonal, and the other one is changing. When they touch, that's a suspicious point. That's a point where F may have a local minima and maxima. Okay, so that's the idea behind Lagrange multipliers. So let me write that here now. So we remember that gradient of G is orthogonal to S at every point. So in particular, at P sub 0, gradient F at P sub 0 and gradient of G at P sub 0 are parallel. Of course, if this is 0, then being parallel doesn't make sense. But again, being parallel, we will write it in a formula. What does it mean that they are parallel? This thing is a constant multiple of this. Okay, if they are pointing in the same direction, one of them may be longer, so that constant will tell us that. If they are pointing in opposite directions, then again one of them may be larger, so we need that constant, but we put a minus sign to show that they are pointing in different directions. We are not interested in how long is this and how long is this, because you see all we want is to have this dot product 0. Okay, so this means gradient of F at P sub 0 is equal to lambda times gradient of G at P sub 0 for some lambda, a real number. Okay, so up to here, I'm assuming that this is different than 0, so they are parallel. So I should put lambda different than 0 here. But here we also have this possibility. So here we allow lambda to be 0, also so that it also covers that gradient of F is equal to 0. Okay, so this turns out to be the necessary condition. Okay, if P sub 0 is going to be a local minima or maxima for this function on the surface S, then this condition must be satisfied. Okay, so now we do exactly what we did in last semester. We look at all points which satisfy this, but here you see we have an extra parameter. So we try to find all P sub 0 and lambda so that this is satisfied. Okay, but in the back of our mind, we are saying that this P sub 0 should be chosen from the surface. Okay, so the equation of the surface is another condition. In fact, it is called the constraint. So we have to solve those two things. Okay, so this is a necessary condition. For P sub 0 on S to be an extreme point for F. Okay, so we also write this in technical terms. This says that G of P sub 0 is equal to 0. Okay, so now these are all the technical requirements. Okay, I want to solve this together with this. Okay, so we have two equations in numerous unknowns. If we are in R3, we are trying to find 3 unknowns here and another unknown here. Okay, so for the picture I draw here, this is in R3, for example, we want to solve 2, in general, nonlinear equations in 4 unknowns. And this is where you are on your own. There is no known method which will solve such things. So you stare at the equations stare back at you. Okay, then an idea comes to your mind. If you are lucky, then you start working on it. And if it's a cooked up example from the book, or it's an exam problem, then it means you stare at the problem for a minute or two, then something obvious will strike you and you solve it. But in real life, okay, you have to take it seriously and start playing. The way to solve such things, if it is not trivial, is to try first whatever comes to your mind. Don't try to get the correct method of solving it in first try. Just try, do all sorts of stupid things that will reveal you the secrets behind the equations, and then you'll find the correct way. That's how you do it in real life. Of course, if the equations are not extremely complicated, you give it to a software. The software, most of the time, will give you some solution or something which looks like a solution, and from there you decipher how to go. Okay, so that is the idea behind the Lagrange multiplier. So now let me write this explicitly, and let me also comment on this local properties. Okay, and when it is guaranteed that you have a solution, okay, so the summary. Okay. So S is given as G of P equals 0. Okay, so now I'm writing it in general dimensions. P can be in Rn. Okay. Gradient of G at P is different than 0 for all P in S. So this is a smooth surface. F from S to R is okay, let's say a differentiable function. Taking a nice function doesn't hurt. Is a function with first partials, so that its gradient exists. Okay, so you see the only thing we use is the existence of the gradient. Okay, so we write the gradient, so we should have something here so that we attempt to solve it. Okay. Solve. So again, before that, here, this is where I have to make a remark. Assume that F restricted to S has global minimum and maximum. Okay, so this is our assumption. This is where you have to look at the nature of the function and nature of the surface S. That tells you whether it has a global maximum and minimum. For example, most of the problems that we can solve are about distances. Why? Because you take the gradient. So if f is your distance function, generally we use the square of the distance function. Otherwise, we have to deal with square roots. If you take the gradient, then this is a linear function. So you are solving a linear function here, and you make g also easy. Okay? Otherwise, you can't easily solve these things. So when you are talking about the distance function, then whatever s is, normally S is a surface that comes close to the origin and then goes away. So it doesn't have a maximum because the surface goes away up to infinity. But at some point, it is closest to the surface, closest to the origin. Okay? So this tells us that there is a global minimum for this problem. Okay? Then we continue with the rest. And sometimes f is not easy to interpret as distance. F is some crazy function, but G is nice. You look at the solution set of G, which is S. It's a closed and bounded set. For example, a sphere. Okay? So if S is a sphere or an ellipsoid or something that you can check which doesn't go to infinity, and it is, since it's equal to 0, if the equations are nice, it is closed, then you again go back to the first weeks of calculus. What did we say? A continuous function. A continuous function has a minimum and maximum on a closed and bounded set. Okay, so that reminds me here that maybe instead of a first partial, let me write that this is a differentiable function so that, okay, we don't have to be very, very sharp on this, which is a differentiable function. Okay, so everything is nice as a differentiable function. Okay, so in particular it is continuous, so that this global minimum x is guaranteed on closed and bounded sets. Okay, so I'll write the comments on this later. Now, assume that this has a global min and max. How do we find it? Using Lagrange multipliers. Solve simultaneously the system gradient of f is equal to lambda times gradient of g at p, and g of p equals 0 for p and lambda. Okay. Now ignore lambda. Lambda is an auxiliary parameter here. The only purpose of lambda is to translate this observation that that the gradient of f and gradient of g are parallel. Okay. After we know that, who cares how long one of them is compared to the other? Okay. Then discard and forget about and throw away lambda. Okay. So in most cases you don't even calculate lambda. Okay. You write everything in terms of well, you eliminate lambda and you get a nice equation. Okay, then evaluate f at each solution. Okay, the smallest value, the smallest of these values is the minimum of f on S, and the largest of these values is the maximum of f on S. Okay? So the idea is very simple. Again, the bottleneck in this system, in this method, is to solve this system. Okay? You appreciate that if f and g are just, even if they are polynomials of degree 4 or 5, then unless the polynomials are carefully cooked up, there's no nice way to solve these equations. But okay, the theory says that the solution is, the min and max is among the solutions there. So let me again make one more write remarks about this. So we are saying, how is it, how do we know that f has a global mean and maximum? Okay, so remark about star. Okay, if S is closed and bounded, f has a global mean and max on S, since f is continuous. Okay, so that's why I wrote differentiable. So now I don't have to add continuity. All differentiable functions are continuous. Okay. Okay. The nature of the problem. Okay, so as an example to here, for example, let me mention example. S is a sphere in R3, for example. Okay. And 2, the nature of the problem dictates that mean or max exists. Okay? So, for example, distance of a plane to a point. Okay? So your function is the distance function from this point to any other point in the plane, in the space, and your G is the equation of the plane. So now you restrict your choice of the other points to this plane. Okay, now you have a function. Okay, now you want to minimize it. I think I'll solve such a problem, and we'll show that it gives you exactly the same number as you would obtain from the formula you get from analytic geometry without any derivatives. Okay, so this is Lagrange multipliers method. Any questions about this? Yes?
Can you use Lagrange multipliers for when P sub 0 is not a local min or max G?
Well, among these solutions, some of the points will be like inflection points. So is that your question? Just like the first one variable case. You take the derivative, equate that to 0, you find the roots, but not all roots are local mean or local max. Some of them are inflection points. So something similar happens here.
We assume that P sub 0 is also a local min or max G or subsets.
Mm-hmm.
Can't use Lagrange methods for when it's not a local or minimum.
Well, if it's not a local mean or local max, then we don't know the behavior of the gradient of f. Okay, we know the behavior of gradient of f is going to be perpendicular to the surface only at these nice points where it has a local mean or max. At other points, so that's what I have this. This is the gradient of g. Okay, so this is the surface. The gradient of g is always perpendicular here. This is the gradient of f. As we move, the gradient of f will change. But at some points, they'll match. The directions will match. Or it may be like this. Again, we call it match. Okay, so these are the points, candidates for local mean or local max. At other points, in particular, if it is not a local mean or max, it will be like this. Okay. What do you mean by f does not pass? F is a function. You evaluate it at every point on the surface. It's not. F is not a curve. F is a function. F is a function. Okay, so this one. F is a function evaluated everywhere. Yeah, we are restricting it here. If you restrict it to some other point, then restriction of f, so we erase that. Restriction of f to that curve, we can write it. We can take its derivative, but then what is it equal to? We don't know. Okay, so what solved this is we know from the fact that it's a local mean or max that this is going to be 0. So we managed to say this is equal to 0. If you do this at some other point, then you get the derivative, which we called phi prime. Okay, we have phi prime equals to this expression, but what is it equal to? Okay, so that's where we crucially need some extra information, and in this case, we derive that information from the fact that f has an extreme point there. Okay. Okay. Other questions? You see, the idea is simple. So all you have to do is to get your hands used to this. Okay. So that's one of the maybe traps in calculus. The ideas have been around for centuries, so now we totally understand these ideas, and when we explain it to you, it sounds very simple. Well, they are simple, but the difficult part is to get used to applying these to actual problems. Okay? So it's easy to write f, g, x, y, z, but when numbers are given, suddenly you are shocked. I don't know why, but that's what happens. Okay? So solve some problems. Let me look at some prepared problems here. The distance of a point, distance of a plane from the origin. Okay, so we have a formula for this. Okay, and we'll show that Lagrange multipliers gives the same answer. The purpose of doing first trivial examples is to build confidence in the problem, in the method. Okay, so it's not a mysterious thing. It gives us what we expect. Okay, so let me do this. Okay, so first example. Find the distance of the plane. So this is x plus y plus z equals 12 to the origin. Okay, so we can solve this problem. Since the equation is very nice, we can solve this problem by drawing pictures. We also have a formula that we derived using analytic geometry without using any derivatives. So so we know the answer. Let's do this using Lagrange multipliers as an example so that we build confidence in the example, plus we see how the method works. If you first do this on a very simple example, then you see how the method is working. Because in more complicated problems, we will get lost in solving those equations. We'll spend 90% of our time in trying to solve that system, and the actual role of the method will disappear. So let me do this. Okay, so it's easy. So here, we know that this distance exists. Okay, so here is the plane, here is the origin. Okay, so there is no maximum, but there is a minimum. So that minimum is the distance. Okay, so our function to minimize is the square of the distance function, square of distance. Okay, so f of x, y, z is x squared plus y squared plus z squared. Okay, the constraint, we call this the constraint. Okay, so this is the condition that P is on S from our previous explanations. The constraint is g x y z equals this expression x plus y plus z minus 12. So equals 0, for example. Okay, so this is our function g, and our condition is that it's going to be equal to 0. Okay, so this is the function to minimize. Okay, so the nature of the problem here tells me that a minimum exists, a global minimum exists. A global maximum does not exist because, you see, the plane goes to infinity. So applying Lagrange multipliers, so we have to take the gradient of f. Gradient of f is 2x, 2y, 2z. Now we remember what we will do with this. We are only interested in the direction of this. So these 2's are not going to change anything. So I write this as 2 times x, y, z, so that my calculations will not be crowded. I'll take this as the gradient of f. Okay, so the only thing it does is either it multiplies lambda by 2 or divides lambda by 2, but we are not going to use lambda anyway. Okay, and then I look at gradient of g. Okay, so this is the function. You see how nice it is. The gradient is 1, 1, 1. Okay, so let's solve this now. Okay, so we said gradient of f equals lambda times gradient of g. So this is x. Well, normally I write it one line under the other. So first entry x is equal to lambda times this, y is equal to lambda, z is equal to lambda. Okay, I wrote this one. So what do we know from here? So from here we know that x equals y equals z. Okay, so it is time to use the constraint. We have one more equation, g is equal to 0. So put these into g equals 0. So what does it say? It says, okay, let me first write this to remind myself what it was. So 3x is equal to 12, x is equal to 4. Okay? So our only, so you see in this case, I didn't even solve for lambda. Okay, so our only candidate is 4, 4, 4. Okay? So we know a global minimum exists. So this gives us the global minimum. Okay? So F 4, 4, 4 is 16, 32, 48. 48. So this is the distance square, d square. D is distance. So d is ben bunu yazmıştım buraya. Buradan bakayım kaç. 4 square root 3. Okay, so you divide it by 3, it is 16. It's the square of 4. 3 is the square of square root 3. So this is the distance. Okay, so now recall we have a formula. We also have a formula. Okay, so distance of the plane ax plus by plus c z equals d to the point x1 y. For some reason we had subscript 1 there, is given by, so this is a formula in the book. So it says d, absolute value of, you put, why am I trying to remember that it's here? Okay. A x1 plus b y1 plus c z1 minus d. Because the formula is generally done when this is on this side. And then you write square root a squared plus b squared plus c squared. Okay? So in our case, here, x1, y1, z1 is equal to 0, 0, 0, and a, b, c is equal to 1, 1, 1, and d is equal to 12. Okay, so you just put these things here. You get 12 over square root 3, okay, because these are 0, you have minus 12, but absolute value is taken. This is 3, and this is precisely this number. Okay, so this is 4 square root 3. Okay? So here, of course, in this problem, the solution of the system is reduced to a minimum. The idea is transparent here. You analyze if you have a global mean or max. So from the beginning, you know that what you are trying to calculate exists. Or maybe the question is find the minimum and maximum distances. You look at the problem, there is no maximum, but there is a minimum. Okay, now I'm trying to calculate this. You take the derivatives, calculate the gradients, set them equal to 0, and now you have two equations. You have this equation and you have this equation, and then you solve them. Okay, so in our case, this took just 1 minute, but normally this is the part where you will spend most of your time. Okay, and then we have candidates here. After that, you calculate this here. What were we trying to find? From the beginning, we knew that there exists a global minimum. There is only one candidate. You calculate the function here, so now you know it is a global minimum. Okay, since there is no other way which tells you whether this is going to be minimum or maximum, you have to analyze the story to decide whether this number you calculate here is minimum or maximum. Okay, in our case, it was clear. We know that this a minimum exists. There is only one candidate, so that's the minimum. Okay, so this is the general idea of this. Okay, let's take a break here, then I'll solve a few more problems.